Welcome back to the deep dive. So you've done all the hard work. You spent months getting the perfect data set. You've optimized your fine-tuning run with all the latest techniques, maybe even used LoRa, and then it appears.
Right, that one single massive file, usually model.safetensors.
Exactly, and it feels like a moment of triumph.
It is, but it's also, the moment the victory lap ends and the real technical marathon begins.
What do you mean by that?
That raw Safetensors file, it's the peak of your training effort, sure, but it is, by its very design, terribly inefficient for any kind of real-world application.
You can't just plug and play.
Not if you want that model to run locally fast, reliably, and critically, without demanding something like 12 gigabytes of VRAM just to process a single sentence. You can't use the training output directly.
Absolutely, and I think that's the core challenge for anyone building these personalized ASR systems. How do you turn that training artifact into a deployment asset that actually respects your hardware?
Especially if you're on, say, a desktop with a challenging AMD GPU or a lightweight laptop or even an embedded device.
The difference between a great fine-tuned model and a deployable high-performance solution, it really lies entirely in that conversion pipeline.
And that's our mission today. We're going to become expert cartographers of that pipeline. We're decoding the whole ecosystem.
Okay, so we're talking Safetensors, CTranslate2, GGUF, ONNX, all of it.
All of it. We'll map out how an AMD user can finally get true, reliable GPU acceleration using CTranslate2. We'll understand why GGUF is so critical for edge deployment and figure out which format wins for speed versus which one wins for accessibility.
This deep dive is really your shortcut. We're hoping to equip you with the knowledge to stop wrestling with slow PyTorch inference and start hitting peak local performance.
Regardless of whether you're running an NVIDIA beast or, wrestling with a tricky ROCm setup.
Let's unpack this crucial stage of ASR development and jump straight into the model format landscape. Where does every journey start?
Well, every modern journey begins with the weights, the ones produced by your training framework, which is usually PyTorch, sometimes JAX. And those files are stored in the Safetensors format.
This format is everywhere now, but I think it's important to understand why the industry made such a swift, universal shift to it just a few years ago.
It is.
The name itself, Safetensors, kind of gives it away, safety. But for anyone listening who maybe wasn't deep in the drama of model serialization, what was the security risk with the old format? Why the big change?
The old standard was serialization using Python's built-in pickle module. You'd get a .pt or .pt file.
Okay.
The problem with pickle is that it doesn't just store data. It stores Python objects and, crucially, the instructions needed to reconstruct those objects when you load the file.
And since Python objects can include custom code.
Exactly. A malicious actor could embed arbitrary executable code right inside the model weights file.
So if you downloaded a seemingly innocent model from a public repository loading, it could, run malware on your machine?
Precisely. It was a massive, just an untamable security vulnerability.
Wow.
Safetensors, which Hugging Face developed, completely solve this by separating the structure from the data. It uses a small, verifiable JSON header to describe the tensors, their names, shapes, data types, and then it just streams the raw binary weight data after it.
So no arbitrary code execution is possible?
None. It's the gold standard now for training and sharing because you can trust it.
That makes total sense for sharing, but why is this secure standard format so poorly optimized for speed during inference? Why can't we just load the Safetensors file and get great performance?
Because Safetensors is fundamentally a general-purpose storage container. It's not an optimized execution graph.
Okay, break that down.
When you run inference directly from a PyTorch Safetensors model, the framework PyTorch has to manage the whole computational graph. And that graph includes all sorts of operations that are not optimized for inference, like dynamic memory allocation, general tensor manipulations. Plus, the weights are often stored in full 32-bit floating point precision.
FP32. And that's highly accurate, but it doubles the memory footprint and the computational load compared to, say, 16-bit, right?
Exactly. But the deeper problem is that high-performance inference engines, they rely on highly specialized, handcrafted code, we call them kernels, to run specific operations incredibly fast.
And PyTorch is more generic.
Right. Specialized engines like CTranslate2 or ONNX runtime, they actually rearrange the model structure. They fuse multiple operations into single hyper-efficient calls, and they pre-quantize the weights to match the specific instruction sets of your hardware. The raw Safetensors file just doesn't have that structural optimization.
So the conversion isn't just about saving space. It's about literally remodeling the computational structure of the model to fit a high-performance blueprint designed for deployment?
Absolutely. Think of Safetensors as the raw architectural blueprint of a house. It has all the information, but it's not organized for lightning-fast construction.
And the converted format.
That's like a prefabricated module, optimized and ready to snap into place instantly.
We can probably categorize these specialized formats into two main families based on the trade-off they're making, maybe the performance family and the portability family.
That's a great way to put it. The performance family is all about raw speed, minimum latency. It generally assumes you have powerful hardware, a dedicated desktop GPU, or a server.
So C-Translate 2 and high-end O and NX would fall there.
Exactly. They're engineered to maximize GPU utilization. The focus is on specialized kernel calls, efficient memory layout, all to deliver the highest possible throughput.
And the portability family is the opposite.
It's focused on deployment flexibility and resource minimization. This is essential for constrained devices, laptops, phones, embedded systems.
That's where you'd find GGUF, T-Flight, Core ML.
Right. They prioritize quantization and CPU optimization. They sacrifice a little bit of that peak performance for maximum accessibility and low energy consumption.
Let's spend a moment on ONNX, the Open Neural Network Exchange. It's often talked about as this ultimate cross-platform bridge. What does it actually do?
ONNX is revolutionary because it provides a hardware-agnostic, standardized representation of the model's computational graph.
Meaning?
When you convert a PyTorch model to ONNX, you're defining the sequence of math operations, matrix multiplications, convolutions, whatever independent of the framework that created them. You end up with a .onx file.
And then something has to actually run that standardized graph.
That's the ONNX runtime, or OIT. And because the graph is standard, OIT can use its huge array of what it calls execution providers. On Windows, it can use DirectML to access both NVIDIA and AMD GPUs. On Linux, it can use the ROCm provider for AMD, or CEDA for NVIDIA.
So that's its key strength. You define the model once, and ORT figures out the fastest way to run it on all these different platforms.
It's perfect if your users are on Windows, Linux, and Mac all at the same time.
But we have to be honest here. All-in-NX is the great generalist. If cross-platform is your number one goal, it's the winner. But for raw speed on one specific architecture, it often falls behind.
Exactly. It's the jack of all trades. That standardization process, while it's great for compatibility, sometimes limits the kind of hyper-optimization you can get with a dedicated transformer-focused format like C-Translate 2.
Which can implement highly specialized kernels just for ASR.
Precisely.
Okay, and let's quickly touch on the extreme end of the portability family, the mobile endpoints.
Right. These are driven entirely by platform optimization, where power consumption is like the absolute number one concern. For the Apple ecosystem, you have Core ML,
which is designed for the Apple Neural Engine.
Exactly. It uses native acceleration, optimized memory access, all for minimal battery drain. And then for Android and General Mobile, TF Lite or TensorFlow Lite is the champion.
And those are just engineered to be incredibly light.
Extremely light. They often support 8-bit quantization right out of the box, letting you run inference even on very old or low-power mobile processors. You need them because a generic inference engine on a phone would just drain the battery and have awful latency.
So the lesson from this first part is clear. The format conversion is a strategic decision. You're aligning the model structure with your target inference engine based on what you're willing to trade: speed, portability, or power.
That's the entire framework.
Yeah.
And now that we've got that down, we can dive into what is probably the most challenging deployment scenario today, getting top-tier performance on AMD GPUs. That requires some very specific choices.
Okay, let's talk about the ROCm challenge. For years, if you were serious about AI inference, you went NVIDIA. You went CUDA. AMD's platform, ROCm, has historically been, well, frustrating.
It's a painful ecosystem story, it really is.
Why did it mature so slowly? Why has reliable inference on AMD been such an uphill battle?
CUDA has benefited from two things: time and focus. NVIDIA spent a decade cultivating it, making it stable, comprehensive. Every major deep learning framework, every specialized inference engine was built with the assumption that CUDA primitives were just there.
Arrows.
It arrived much later, and its support, the drivers, the libraries, the documentation, has often lagged behind, especially in really critical areas like the compiler tool chain and, stable backward compatibility.
So if a developer tries to optimize an ASR model for ROCm, they're often facing this moving target of driver versions and incompatible libraries.
Exactly. And unlike CUDA, which is generally pretty seamless, deploying ROCm often requires you, the user, to meticulously match your OS kernel, your specific GPU architecture, and the version of the ROCm stack you download. So just a lot of complexity.
Which makes reliable production deployment incredibly difficult.
It does.
So this is where we need a specialized, reliable solution for ASR. And the one that stands out for AMD users is Faster Whisper, which is built on C-Translate 2. Why has this combo succeeded where others have stalled?
Faster Whisper, using that C-Translate 2 backend, is the Tier 1 solution for a reason. It is engineered with laser focus. C-Translate 2 is not a general-purpose framework. It is purpose-built exclusively for efficient transformer inference.
And because of that singular focus,
they were able to invest heavily in creating highly optimized ROCm kernels.
Let's break down that optimization. When we say C-Translate 2 offers 3 to 4 times faster inference than the original PyTorch code, what's it actually doing to get that speed, especially on AMD hardware?
There are 4 core things happening. First is op fusion and specialized kernels. Instead of running individual operations one by one, C-Translate 2 fuses common sequences like the matrix multiplications and the attention mechanism into a single, highly optimized kernel call.
Which cuts down the overhead of launching tons of tiny tasks on the GPU.
Dramatically. Second is pre-quantization. The weights are converted to lower precision, like Int8 or Int16, before runtime. This reduces memory bandwidth usage.
And that saves memory and speeds up data transfer, which is a huge bottleneck. What about the decoding process itself?
That's the third mechanism.
Right.
Optimized beam search. Whisper uses beam search to find the most likely sentence. C-Translate 2 re-implements that logic and the greedy decoding paths using custom C++ implementations, which are way faster than the Python PyTorch equivalent. And finally, and this is the most critical part for the hardware, it has handcrafted ROCm and CUD kernels tailored to the architecture. For AMD, the C-Translate 2 developers have specifically ensured reliable support for RDNA architectures, the GFX 100 series, like the RX 7000s, and the GFX 130 series.
That focus approach bypasses a lot of the general performance issues that plague other frameworks.
It does, it just works.
So the actionable step for an AMD user is crystal clear: fine-tune in PyTorch, convert to the specialized C-Translate 2 format, and then use Faster Whisper.
Right. It minimizes the variables. You're using a tool designed for your task and optimized for your architecture. It just drastically reduces the chance of hitting those environmental issues.
Now let's contrast that stability with the other big player in local ASR, Whisper.cpp.
Yeah.
It's amazing for CPU inference, but its AMD GPU support is, well, it's experimental, and it's prone to that notorious silent fallback pitfall.
Whisper.cpp is a marvel of C++ optimization for sure. It's designed for low memory and fast performance using things like SIMD and AVX on the CPU.
We'll get to those.
But yeah, for CPUs, it's perfect. Its GPU acceleration via ROCm HIP, though, is often unstable, and the silent fallback is exactly what it sounds like. You run a transcription expecting GPU acceleration, but if the ROCm stack fails to initialize,
Maybe because of a missing library or a driver mismatch?
the engine doesn't throw a big loud error. Instead, it just quietly redirects that massive computation load right back onto your CPU.
And the user sees pretty good performance because the CPU optimization is great, but they look at their GPU monitor and see 0% utilization.
Exactly. They think maybe it's just really efficient, but in reality, their CPU is pegged at 100%, and they're missing out on the 3x or 4x speed up the GPU is supposed to provide.
And fixing this often means users have to dive into environment variables, like manually setting HSA override EPSA version. Why is that even necessary?
That tells you everything about the maturity of the ecosystem. When AMD releases new hardware, the stable ROCm package often takes months to officially recognize the GPU's architecture ID. So users with brand new cards have to manually tell the system, hey, pretend my new card is actually this older, officially supported card.
That's a workaround, not a solution.
Not at all. And it's a symptom of an ecosystem that's struggling to provide consistent, up-to-date integration. That's why C-Translate 2 is the clear Tier 1 choice for production speed on AMD.
So where do things like PyTorch, ROCm, and ONNX runtime fit in?
They're fallbacks. PyTorch with the ROCm backend is great for quick prototyping and debugging because there's no conversion step. It works right on the Safetensors. But it's usually the slowest and has the highest VRAM requirements.
And ONNX.
Great for portability. If you need a model to run on your work laptop with Windows and DirectML and your home desktop with Linux and ROCm, ONNX is a workable solution.
But if we're comparing pure speed on ONNX versus C-Translate 2 on ROCm,
C-Translate 2 usually wins. ONNX runtime has to support every kind of model, CNNs, LSTMs, transformers. Translate 2 only supports transformers. That narrow focus lets them dedicate all their resources to optimizing the specific operations Whisper needs, and that results in better latency on AMD. Translate 2 is the specialist. ONNX is the utility player.
We've been focused on peak performance on powerful hardware. Let's shift to the opposite extreme, getting models to run reliably on resource-constrained devices. Laptops, older CPUs. This is the world of quantization where GGUF is king.
Right, this is a huge area of interest because most people don't have a high-end GPU. They just want their fine-tuned model to run instantly on their MacBook or their desktop CPU.
And to do that, we need quantization. We're aggressively reducing the precision of the model weights.
Exactly. We start with FP32, that's 32-bit floating point, the standard for training. High fidelity, but huge memory use.
Then the first step down is usually FT16?
Yeah, 16-bit floating point. That immediately halves the memory footprint with almost no loss in accuracy for modern models. Then we get aggressive. We go to INT8, 8-bit integers, or these various custom schemes like Q4K or Q5K, which use clever methods to pack weights into 4 or 5 bits.
And the trade-off is a tiny, tiny loss in accuracy for a massive saving in memory, right?
That's the game.
Yeah.
You might sacrifice, 1% or 2% your word error rate to reduce the RAM footprint by 75% or 80%. It's the necessary exchange for running on the edge.
Which brings us to the formats that the Whisper.cpp ecosystem pioneered, starting with a legacy format, GGML.
GGML, or Georgy Gerganov machine learning, was the original format that made all the CPU inference possible. Its strength was its raw efficiency. It gave us the tools to quantize models and load them into RAM for the CPU.
And it was built to leverage modern CPU instruction sets. We should probably explain SIMD and AVX here.
We should. A GPU gets its speed from having thousands of tiny cores running in parallel. The CPU has fewer cores, but it can achieve its own kind of parallelism through SIMD or single instruction multiple data.
And instruction sets like AVX, advanced vector extensions, let a single CPU instruction operate on multiple pieces of data at the same time.
Precisely. So instead of one multiplication at a time, the CPU can do 8 or 16 at once in a single core. GGML was designed to align the quantized weights perfectly with these SIMD and AVX lanes.
So even without a GPU, a modern CPU could transcribe audio surprisingly fast with minimal RAM.
It could. You'd use the .bin extension. But the old GGML format had a major flaw that made it a maintenance nightmare.
Which led to GGUF. What was the central problem with GGML?
It had no structure, no metadata. A GGML file was essentially just a blob of weights. It was not self-describing.
Meaning?
If you quantized a model using a Q5K scheme and shared that .bin file, the file itself told you nothing about the architecture it came from, the exact quantization settings used, or the tokenizer instructions.
So if I downloaded a GGML model and my version of Whisper.cpp expected a different quantization format or a slightly different model structure, what would happen?
You were heading for a compatibility disaster. You'd get silent, bizarre errors, or the runtime would just guess wrong and give you corrupt output or just crash.
So you had to manually track all that metadata somewhere else.
In a README file, a forum post, something. If you came back to that file 6 months later, you might have no idea how it was made. It made long-term maintenance impossible.
It sounds like a recipe for catastrophic configuration failure.
It was, and GGUF, the GGML universal format, solved this so elegantly. GGUF, with the .guf extension, created a self-describing container. It embeds all the critical metadata right at the start of the file. The model becomes completely self-sufficient.
Give me a concrete example. What kind of metadata does GGUF embed that GGML was missing?
Everything you need. The specific model architecture, like Whisper Large v3, the full vocabulary list for the tokenizer, sequence length constraints, and most importantly, the exact quantization type used. It explicitly tells the runtime, I was quantized using the Q4K method. My context window is 30 seconds, so please use this specific decoding path and these specific kernels.
So the runtime knows exactly how to handle the weights, which minimizes the risk of a version mismatch.
Exactly. It ensures reliability. If your runtime doesn't support the Q8 quantization listed in the header, it can throw a clear, informative error. It won't just silently fail. GGUF is the undisputed modern standard for any new project targeting CPU or edge deployment because it provides that critical reliability and future-proofing.
So it's not that GGUF is inherently faster than GGML's tech, but it's way more reliable, which makes those quantized models actually usable in a production setting.
That's the key distinction. It transforms quantization from an unreliable hack into a stable, deployable technology. Okay, we need to pull back now and address a pretty big misunderstanding that a lot of new users in the local AI space run into, and it's all about hardware monitoring.
You're talking about the high GPU utilization numbers during inference.
Yes.
We see this all the time. A user looks at their monitoring tool, they see their GPU spike to 90%, 95%, sometimes 100% during a transcription, and they panic. They think they're bottlenecking or overloading their expensive new hardware.
And that panic comes from their experience with continuous workloads, like gaming or video rendering. So let's just set the record straight right now. Is 100% GPU utilization during AI inference a problem?
And the answer is?
No. It is the desired optimal state of affairs.
Walk us through the why on that. Why is this different from a video game where 100% GPU usage might mean you're bottlenecked?
Because AI inference, especially running a transformer like Whisper, is an intensely bursty workload. The task isn't continuous, it happens in these discrete, sudden bursts.
Right.
When the model processes a new chunk of audio, it needs the GPU to perform a massive sequence of matrix multiplications, the forward pass, as quickly as humanly possible. When that GPU hits 100%, it means it's fully saturated with calculations, running at peak efficiency for that single moment.
So the GPU is just doing the job it was bought to do, using all its available power for a fraction of a second.
Precisely. If you're doing streaming transcription, the pattern is predictable. GPU usage spikes to 100% for maybe half a second to 2 seconds as it processes a 30-second chunk of audio.
And then it drops right back down to idle.
Instantly. Back to 0% or 10% while it waits for the next chunk of audio. If you didn't see 100% utilization during those bursts, it would mean your CPU or your memory bus was bottlenecking the data feed to the GPU.
That's a critical reassurance. You shouldn't be aiming for 60% GPU usage. You want maximum utilization during those compute cycles.
Absolutely. The metric you should be focused on isn't utilization percentage, it's the real-time factor, or RTF.
Which is the time it takes to transcribe the audio divided by the length of the audio itself.
Right. An RTF of 0.1 means it takes 1 second to transcribe 10 seconds of audio. If your RTF is low, you're winning, regardless of what the utilization spikes look like.
Okay, that brings us to VRAM. We need to clarify the difference between VRAM capacity and GPU compute power. They govern different things.
They do. VRAM capacity is strictly a prerequisite. It determines the maximum model size you can load. If the weights, plus all the temporary tensors you need for inference, exceed your VRAM, the model will fail to load or it'll spill over into your much slower system RAM.
Which kills performance.
Kills it. GPU compute power, the raw shader count, the clock speed, that determines how fast the model runs. That's what dictates your RTF. You need enough VRAM to load it and enough compute to run it quickly.
Let's give the listener some concrete numbers for Whisper's VRAM needs when using common quantized schemes like Q4 or Q5.
Thanks to that aggressive quantization, the requirements are remarkably low. A quantized Q4 version of the Whisper medium model, which is often a sweet spot for balance, only needs about 900 megabytes of VRAM.
Under a gigabyte.
And stepping up to the biggest open source model, Whisper Large V3, that needs about 1.8 gigabytes of VRAM when it's quantized to Q4.
That puts even a mid-range consumer 8GB GPU firmly in the excellent tier for local ASR. You can run the most accurate Whisper model and still have capacity to spare.
It completely democratizes local ASR performance. You don't need a top-tier card just to get accurate transcription. If you have 8 gigs, you can run Large V3 locally and privately.
So let's talk long-term hardware strategy. For someone focused on STT and other local AI tasks and considering the complications with the AMD ecosystem, what's the recommendation? Is it a dual GPU solution AMD for display, NVIDIA for compute, or should they consolidate?
For anyone prioritizing long-term stability and peak performance in the AI space, the clear recommendation is to consolidate into a single powerful NVIDIA GPU, ideally with 12 GB of VRAM or more, like an RTX 4070 Ti Super 16 GB.
Why is the single card superior even if someone already has a working AMD card they could use?
Because dual GPU solutions introduce immense system complexity. First, driver management. Running 2 different vendor drivers, AMD Adrenalin and NVIDIA CUDA, at the same time often leads to instability and update conflicts.
Right.
Second, system logistics. You're doubling the power draw, increasing heat, complicating cooling. And third, PCI lane contention. If your motherboard splits the critical PCI lanes between 2 cards, you might find your compute card isn't getting the bandwidth it needs.
The single card just streamlines the whole stack.
Completely. You get access to the mature, stable CUDA ecosystem, which reduces your installation and debugging time to almost 0. The performance gain from that stability just far outweighs the cost savings of trying to duct tape 2 different cards together.
And a quick final comparison for desktop ASR is the best hardware A GPU, an NPU, or a TPU?
The GPU is still the clear and superior choice. NPU's neural processing units are fantastic for energy efficiency on phones or low-power laptops, but they're generally slow, and their software support for off-the-shelf models like Whisper is often lacking.
And TPUs?
TPUs, tensor processing units, are built for massive cloud training or Google-specific inference needs. They're completely impractical for a desktop user. The GPU just strikes the perfect balance of massive parallel compute, mature software support, and accessibility.
We've covered the deployment formats. Let's go back to the model itself and the magic of transfer learning. We know models like Whisper were trained on a staggering amount of audio, 680,000 hours.
A truly mind-boggling amount.
So here's the fine-tuning paradox. How can a tiny data set, maybe just 5 to 10 hours of your own specialized audio technical jargon, unique accents, update that massive base knowledge without accidentally destroying all the general linguistic understanding it already has? The fear of catastrophic forgetting.
That is the fear. And it's a valid one if you train incorrectly. Catastrophic forgetting is what happens when you train a model on a new task so aggressively that it just overwrites the weights responsible for its original general knowledge.
Like trying to replace 90% of the books in a library with specialized manuals?
You lose all the general knowledge. It's a disaster.
So how does fine-tuning prevent this architectural vandalism?
We use two core safeguards. The first is the learning rate. The second is architectural selectivity.
Let's start with the learning rate.
When OpenAI trained Whisper from scratch, the model started with random weights. It needed a high learning rate, something in the range of 10 to the minus 3 or 10 to the minus 4, to make large, rapid adjustments and just find the general landscape of human speech.
But when we fine-tune, the model already knows 99% of what it needs.
So we dramatically reduce the learning rate. We often drop it down to 10 to the minus 5. Or even 10 to the minus 6.
And what does that tiny, cautious learning rate actually do?
It ensures the model makes only microscopic corrective adjustments. It's not bulldozing the existing knowledge. It's gently nudging the model toward a specialization point for your voice and your vocabulary.
It's just modifying existing weights enough to fix the errors specific to your domain.
Like accurately distinguishing between kernel optimization and kernel optimization when spoken in your specific accent.
And then there's selectivity, the idea that some parts of the model are more robust and shouldn't be touched.
Precisely. The transformer is layered. The initial layers of the encoder are feature extractors. They learn universal acoustic properties like what is a foam or how does sound decay. These layers are universal, so we often freeze them during fine-tuning.
That's where the general knowledge is held.
And the largest, most impactful changes happen in the later layers. The decoder layers and the final output projection layer. The decoder handles linguistic sequence and context, and the output projection maps the internal representation to specific vocabulary tokens.
That's where your specialized jargon lives.
Right, so fine-tuning focuses the effort there, leaving the universal acoustic features intact.
That sounds incredibly efficient. But the techniques have moved on even further with things like LoRa. Let's talk about the efficiency gain there.
Low-rank adaptation, or LoRa, is revolutionary because it moves beyond just minimizing changes to the original weights, which we can call W. It avoids changing them altogether.
Ow.
It's an additive method. When training, instead of calculating the update to the original weight matrix W, it introduces two tiny low-rank matrices, A and B.
Okay.
And it trains them. The resulting product, A times B, is the update.
So the model's core general knowledge, W, is perfectly preserved, and all the new specialized knowledge is stored entirely in these much smaller adapter matrices.
Exactly. And the efficiency gain is enormous. A large model might have billions of parameters in W. When you fine-tune fully, you might train hundreds of millions of parameters. With LoRa, you might only be training a few million parameters inside A and B.
Which drastically reduces the memory needed for fine-tuning.
It speeds up training significantly. It's specialization bolted on, perfectly preserving the base model's integrity.
This all ties back to our main topic, local performance. What is the strategic value of applying this fine-tuning process to smaller models, like Whisper Tiny or Small?
This is the crossover effect, and it is the single most important strategic takeaway for local deployment.
Okay.
Smaller models, by their nature, have less capacity. They start with a higher word error rate than the large model, because their limited structure forces them to generalize more. They have the most room to improve from specialized training.
So the specialized training gives a disproportionately larger accuracy jump to the small model than it does for the already super accurate large model.
Precisely. For your domain, your accent, your technical vocabulary, a fine-tuned Whisper Small can often approach or even match the absolute accuracy of a stock, off-the-shelf Whisper medium model.
You're capitalizing on specialization to compensate for the model's general lack of capacity.
And the ultimate benefit is you're running a model with medium-level domain accuracy, but at the dramatically lower compute cost and latency of a small model, which might only need 500 millibar of VRAM.
The practical value is just unbeatable.
It is. You get highly accurate, personalized ASR running locally, privately, and fast. Compare that to sending your audio to an expensive cloud API using the stock large model, waiting on latency, and paying constant costs. For daily utility, the fine-tuned small model is the optimal choice.
Let's quickly revisit the data prep for this. You mentioned the counterintuitive strategy of recording clean audio and then adding controlled noise. Why is that better than just recording in a noisy environment?
Because you want the model to learn the signal, which is your voice, and noise robustness as two separate, manageable concepts. If you just record in a chaotic coffee shop, the noise profile is inconsistent, and it's all mixed in with a speech signal. The model struggles to separate the two.
I see.
The best strategy is to record clean, high-quality audio in a quiet setting. Then programmatically, you use tools to apply controlled noise augmentation, adding specific, standardized noise profiles like white noise or street sounds at defined signal-to-noise ratios.
So the model learns noise robustness systematically.
Much more efficiently and effectively. And just remember, because of Whisper's fixed architecture, your audio chunks must be kept short, ideally 10 to 30 seconds, and never ever go over that 30-second architectural limit. So we've established that mastering ASR deployment is really a strategic game of trade-offs. You have to choose your format based on your goal.
Right. Raw speed and proven AMD support means C-Translate too.
Maximum cross-platform compatibility that requires ONNX.
And reliable low-resource deployment relies on that modern self-describing GGUF format.
We've also replaced the fear of 100% GPU utilization with the knowledge that it's a sign of efficiency during those inference bursts.
And we confirmed that an 8GB GPU has more than enough capacity for running even the most accurate quantized Whisper models.
And most critically, we confirmed the strategic value of specializing small models. Through the intelligent use of small learning rates and LoRi, you can get the accuracy of a stock medium model while benefiting from the speed, the cost, and the privacy of a local small model.
Your ultimate ASR success really hinges on matching that perfectly fine-tuned model with the optimal format for your target hardware.
So here's our final provocative thought for you. You now have the architectural map to create a highly accurate, personalized ASR experience tailored precisely to your voice, your technical vocabulary, and your accent.
Given that the fine-tuned small model is demonstrably faster, cheaper, and more private than the stock medium model running in the cloud.
Which small model should you prioritize converting to the reliable GGUF format today for use on your phone or your lightweight laptop?
Don't let that huge Safetensors file just gather digital dust. Apply these format conversion and optimization techniques now and truly unlock the efficient, personalized potential of your local ASR models.